Hello and good morning everyone. Welcome you all for the NPTEL online course on economic operations and control of power systems. Today's lecture will discuss about control of generations. So, the optimal dispatch and scheduling of generation establish the best operation point with respect to economics, right? So, based on economic load dispatch, we will be getting the best operation point which is economical, and OPF will also help us understand that ultimately whatever the generation that we are planning, it should be also economical including the system constraints. So, the operating point must be implemented via generation control. Let us say you give a command, this is the generation output that need to be achieved. So, how do you achieve it actually? At the end of the day, there should be some control loops acting together such that you would be able to manage that specific generation from a particular generator. Also, if there is a change in load conditions, these generators would be able to adjust their generator output such that the change in load will not have any effect in change in frequency. So, this is the objective. So, local generator control for each individual generator, because ultimately in the root level each generator output will be changed such that you will not feel any change in system frequency. Energy control center for the control of a large utility and the flow of power across interconnections to other utilities, right. So, like there are multiple utilities, they are connected together, right, using tie lines. So, you should ensure that the frequency will be managed here also, but ultimately if there is any tie line power exchange that need to be taken place, that will be also be done such that even in that case the frequency will be managed properly, maintained at a nominal value. So, regional control over several utilities and the independent power producers, IPPs, that is ISO, independent system operator, will be playing a crucial role in power exchange, and RTO, regional transmission system operator, will ensure that proper control action is taken place at the regional level, at the national level, such the interstate power control will be proper, right. So, many generators supply power to the transmission system. In reality, it is not one single generator which is managing the entire power. So, it is a multiple generators, right. So, consumer loads are constantly changing the power level because you keep on changing the loads in your home, switching on the lights, switching off ACs and all these things. Perturbations will be always there from the distribution load side. So, some control means are needed to allocate the load changes to the generator. There should be some means where you reflect the changes in the load on the generator side. So, a governor in each unit maintains a mechanical speed basically. The governor is meant to maintain the speed, that is what is called a speed governor. If you maintain speed, then automatically you will also maintain the frequency. So, basically ultimately what you need to do, if there is a change in load, you need to adjust the speed by using speed governors. So, you see here, this is what a simple block diagram you can see, there is a entire power system network, right. So, there are multiple generators connected. Let us say here we are giving an example, generator 1 and generator 2, the turbine generator unit combination is there, and you are sensing the power output of individual generator and you are also measuring the system frequency, right. If there is a change in system frequency, you would take an appropriate control action. There is a common overall control system is there. From there you would dispatch individual control signal to individual generator such that a change in system frequency will be managed by all the generators. Otherwise, let us say you can take a control action and push one single generator or couple of generators to manage, then it will be overburdened, it will not be a justice for sharing change in load, right. So, ultimately the change in frequency which is occurring due to change in load need to be managed by all the generators, henceforth individual control signal is being generated from the main control center and the appropriate action is being taken place. And also measurement of tie line flows to neighboring system is also managed by this generation control system, right. We need to define different models. So, first we will start with generator model. So, here is a turbine. So, the input could be steam or whatever, the water, or could be gas or whatever, anything, renewable energy also, you can take renewable energy also. So, whatever is the input, there is a force which is making the turbine to rotate, and that is coupled with a generator through a shaft, right, and ultimately you are getting electrical energy. So the turbine is producing mechanical energy. So let us say this is a mechanical torque that is seen, but if there is a load connected, then let us say this is a utility, if there is a load connected, there will be opposite torque being applied, which is due to the effect of Lenz's law, you can say, So the electromagnetic torque is being reflected, right, such that it would try to reduce the speed if there is more load. So then there will be change in frequency. So that we will discuss how, in spite of there is a load, we will keep manage the frequency at nominal value. So these are some of the parameters. Omega is rotational speed, alpha is rotational acceleration, delta is phase angle of a rotating machine, and T net is net accelerating torque in a machine. This is the difference between mechanical torque and the electrical torque. So mechanical torque exerted on the shaft by the turbine and electrical torque exerted on the shaft by the generator, right. So P net is net accelerating power which is again the difference between mechanical and electrical, and I is moment of inertia for the machine. Any machine has its own inertia, that is indicated by I, and M is angular momentum of the machine. So these are the parameters which are important for generator model. So basic relationship, we will start with the basic. So acceleration principle is T net is nothing but the change in mechanical, difference between mechanical and electrical power. T net is moment of inertia into angular acceleration, right. So momentum principle indicates M is equal to omega into I. Omega is angular rotation speed and I is the inertia, right. This is momentum. And power equation, P net is equal to speed into torque, this mechanical way of expressing the power, speed into net torque. So general shaft equation is omega is equal to omega naught plus alpha t, like you have V is equal to V naught plus alpha t, similar thing, and delta is equal to delta naught plus omega naught t plus alpha half alpha t square. So deviation from nominal, the rate of change of angle is nothing but change in frequency, right. So that is what is expressed here. So change in frequency, this also expresses alpha into t. So relation to torque, T net is equal to T mechanical and minus T electrical. T net is nothing but I alpha, which we have already defined. So this is equal to I alpha, and I alpha is nothing but I into alpha, it can be expressed as d by dt of del delta, that is d square by dt square of delta del delta. This is delta omega, that is nothing but alpha is nothing but 1 by t, right, ultimately alpha is equal to 1 by t. So that means again you are differentiating. So you will get d square by dt square of del delta basically into I, that is T net. So deviation of power is P net is equal to P mechanical minus P electrical, that can be expressed as omega into, you replace T net by I into d square del delta by dt square. So the resulting swing equation is P mechanical minus P electrical, so that is nothing but M into d square dt square d square by dt square of del delta, right, because omega into I is nothing but your moment of inertia. Now apply Laplace transform. This is during steady state, mechanical torque is equal to electrical torque, that is why we have mentioned T mech 0, this is steady state. And T net can be expressed as T mechanical minus T electrical plus if there is any change, that is reflected as delta T mechanical minus delta T electrical, because T mechanical is equal to T electrical, so this is gone. So you will get only this much, delta T mech minus delta T electrical. So P net is nothing but omega into this, so you will get delta P mech minus delta P electrical, or delta P mechanical minus delta P electrical is nothing but M into d by dt of del omega, right, and delta P mech minus delta P electrical can be further reduced as d by dt can be expressed as S in Laplace domain into del omega. So block diagram, so this is a difference, delta P mech minus delta electrical into 1 by ms will give you delta omega, this simple control loop. Now we will go to load model. Electrical load consists of varieties of devices. Purely resistive load, nowadays polytronics loads are also there, which are non-linear loads, and motor loads, dynamic loads, rotating machines. So motor loads dominates the mix of loads basically, because most of the industrial loads are motor loads. Motors exhibit a variable power frequency characteristics. Model of the effect of a frequency change on the net load drawn. That means if there is a change in frequency, that is also reflected in terms of change in power output from this from these machines, right? So that need to be also taken care in the control loop. Frequency dependent loads, their performance depends upon the change in frequency. So delta PL frequency is equal to D into delta omega, right? So D is expressed as that factor as a percentage change in load per percentage change in frequency. So percentage change in load means actually delta PL here, percentage change in load with respect to percentage change in frequency, right? Due to some reason, if there is change in frequency, because of that there will be change in power output from these loads. So that value of D must be converted to the system power base for system level studies. So basic frequency dependent load, delta omega into D is delta PL. Rotating mass and load as seen by prime mover output, you see here delta Pmech minus delta PL, right? This is this was the earlier one, this loop was not there, into 1 by ms was delta omega, this we got from the swing equation. Now to this there is also frequency dependent load if it is there in the system, so that you need to be this need to be also reflected in this overall control loop. So delta omega into D again is delta PL, that is what we have added this loop, there is another term which is adding. So delta P mechanical, and you can reduce the control loop now, right? So this can be added together because they are connected in parallel, that means you will get 1 by ms plus D. So this is nothing but your delta P load, and you will get this overall control loop. So the net change in electrical power load is P electrical is delta P electrical is equal to delta PL plus D delta omega. D delta omega is due to frequency dependent loads. There will be some loads also which are not frequency dependent loads. Even though there is change in frequency, these loads will not have any impact. Special effect due to change in frequency is not seen here. So henceforth the total net electrical power load changes effect due to change in load due to frequency dependent loads and just normal loads which are not frequency dependent loads. So let us take an example. Consider an isolated power system on a 1000 mega volt ampere base. So 600 MVA generator is considered, where momentum is 7.6 per unit megawatt per unit frequency per second on the machine base, and 400 MVA is the load which is considered. So the load changes by 2% for a 1% change in frequency. So here we are getting an idea about what is D. D is equal to 2% by 1% change in load with respect to change in frequency. So D is equal to 2 basically. Suppose that the load increases by 10 MVA. What is the transient response of the system frequency? So change everything to the per unit level now, that will be easy for our analysis. M is equal to, we have given 7.6 megawatt means is 600 by base is 1000. So we will get 4.56 per unit. D is equal to 2 into, we just calculated 2, this into this is at 400 MVA, this is the load, and divided by 1000 you will get 0.8 per unit. And delta PL is the change in load which is increase in load, this is 10 MVA with respect to base, this is 0.01 by S, right, because this is changing with respect to time, so 0.01 by S. That is delta omega S is equal to delta PL into 1 by ms plus D according to our control loop, that is 1 by m is 4.56 and D is 0.8. So this is your delta PL, and then this is your delta omega, and then this is in Laplace domain changed to time domain. So you will get this term. So the change in frequency with respect to time is indicated here as a transient response. Next we will move to prime mover model. right. The prime mover drives the generating unit, it could be steam turbine or a hydro turbine, whatever. So there is a steam input and that is regulated using a steam valve, either you can, even though if there is steam input, you can close it so that prime mover may not be getting any input at all, so that control is there. So again then based on how much you open, based on that you will get the mechanical power output. So modeling must account for control system characteristics. Example, boiler and steam supply. You see here, model of the non-reheat turbine. So delta P valve into 1 by 1 plus STCH is delta P mechanical. That means the mechanical power output will be indirectly depending upon how much the steam valve proportionately will open, right. So that is expressed in terms of this actually. Delta P mechanical is equal to, this is the transfer function 1 by 1 plus STCH, because there will be a charging time constant is involved when we open it, and per unit change in valve position from nominal value, delta P valve, right. So now this is your prime mover model. The delta P mechanical is coming and it is dependent on the P valve. So that also we need to be included when you consider the overall control function. So delta P valve into 1 by 1 plus STCH will give you delta P mechanical, and this subtracted by delta P load multiplied by 1 by ms plus d. This is due to the swing equation that we are getting this, and dependent loads, frequency dependent loads, you are getting delta omega ultimately. Now governor model. The governor compensates for change in shaft speed. Changes in load will eventually lead to change in shaft speed basically, right. Change in shaft speed is also seen as a change in system frequency. So simplest type of control is the isochronous governor. Isochronous means there is only one generator connected to the system where there are loads present. Now how it works? Now there is a steam input which is regulated through steam valve to a prime mover, and there is a rotating shaft. Let us say there is a generator and all is there. Now you use a tachometer to measure the speed, and there is a nominal frequency, let us say it is 50 hertz for India, that need to be regulated, and let us say there are so many loads which are connected here in actual system. So the output of this may be connected to a generator, this is generator, and generator output is connected to various loads, correct. If there is a load which is connected to this generator output, so because there will be electromagnetic torque, opposing torque, it will try to pull the frequency down because speed is decreasing now. If there is increase in load, speed will decrease, because of which there is a difference which is created from the nominal value, right. There is a difference, and this is being minus omega w reference because speed is decreasing. So this output is negative basically, and you again multiply by negative, that means it is positive here, right. So there is a gain just to increase the control action. So basically this is PI controller, there is an integral controller. Integrator will ensure that steady state error will be 0, and ultimately what is the action? Action is your change in load will have to be reflected as change in steam valve output, because of which the input will be increasing now. So the entire thing is positive. Positive means what is there? Open the valve. Open the valve. You open it even wider so that more steam can go inside. Let us suppose the speed is decreased, speed is increased because load has decreased. So this output will be positive. This is positive here, this is positive, and this is negative, and ultimately you will close the valve. So this is with respect to one single generator, it can manage it quite comfortably. What will happen if there are multiple generators, because in actual power system and they are connected to an infinite grid, there are multiple such generators which are running in parallel. So you can either just put a burden on one single generator, take the control action, just keep one generator to cater to the requirement, change in load. That will not be possible actually in real sense. No one single generator is having sufficient capacity to manage to the entire system. So you need to change, this reflection of change in load has to be distributed across different generators. So to force frequency error to 0 requires the use of an integration that we have discussed. The isochronous governor cannot be used when two or more generators are electrically connected to the same system. What will happen is there is a fighting between generator governors for system frequency. Everyone wants to pull actually. So this will lead to system instability and problems with load distribution between generators, and also you are not judiciously distributing the change in load among different generators. So these are the two issues. So a load reference control provides settings for both the frequency and the desired power output basically, right. So a new input, the load frequency signal, controls the desired power output. A feedback loop contains a gain R that determines a speed droop characteristics. So basically a speed droop characteristics, the governor or a droop characteristics will help to ensure that during normal and transient conditions the load is shared among the multiple generators. I will explain you in detail. So the speed droop function handles the load sharing between generators. There will always be a unique frequency at which the system loading will be shared among the generators, right. The gain R is equivalent to the per unit change in frequency for a 1 per unit change in power. This is what is droop coefficient, change in frequency with respect to change in power, and individual generator has its own droop coefficients that depends upon its size and capacity, right. Now what is happening, this is a general control loop characteristics. So we are adding this extra term now. There is a load reference set point, or it is also considered to be governor set point. No. So because at this load reference set point you will be able to appropriately generate a rated frequency, a nominal frequency, right. So now there is a summation block, as you can see here, there is a summation block. So delta P valve, how the valve position output is again checked with the load reference set point, and this output is connected to the droop coefficient, and this is again connected to the main summation block here. So what is happening, so let us say there is a decrease in load, or let us say there is an increase in load now. The frequency is decreasing, speed is decreasing. So that means this output is negative, this is what I told. In case of single generator, the entire burden was on one single generator, that is what we had discussed in the last slide. Now what will happen, because of the presence of the droop, this need to be divided. That means you cannot have 100% sharing on one single generator. That means whatever is the sign that you are getting here, this is negative, right. So negative into negative, this will be positive here, at this side this is positive, but here what you are getting is this is a negative. So positive negative, that means earlier let us say it was, for example, 100% in the first case without this droop characteristics included, let us say it was 100%. 100% in the sense 100% reflection on one single. Now because of the droop, this will reduce the sharing on individual generator. It could be 80%, 50% or 30%, 20%, it could be any number, but it will be less than the previous number, and that will be shared based on their capacity. So again this will be applied to integrator control. So appropriate valve opening is being catered such that all the generators which are running in parallel will share the change in load, and the frequency will be adjusted with a cumulative effect basically. So the same block diagram is being simplified here, so this is P reference, this is load reference set point, and then there is a droop coefficient and delta omega minus this, and this is the integrator control and is applied to the valve. position basically. This is the same thing which is represented in a different manner. You can change the you can shift this basically block diagram reduction techniques, so that you will be able to obtain a transfer function ultimately. So we are just using block diagram reduction techniques. So R is shifted here, this is 1 by R, then you will get this term 1 by 1 plus S kgr whole inverse, and ultimately this is what you are getting, where 1 by kgr is reflected as 1 by S 1 plus STG. So this is what I was interested to show actually, speed droop characteristics. So if there is a increase in power output by a generator, you can say here there is a change in frequency, drop in frequency basically. So if there are two generators which are sharing the power, unit 1 power output, this is unit 2 power output. So you can see here, this is the nominal frequency, let us say this is 50 hertz. So for that, the power shared by the first generator is P1 and the power shared by the second generator is P2, right. They have different droop characteristics. So if the load is increased, then the power output from the first generator is changed from P1 to P1 dash, and power output from the second generator is changed from P2 to P2 dash, such that P1 dash plus P2 dash will be is equal to change in load. But as a result of this, now both of these generators are agreeing to operate at a different frequency which is different from nominal frequency. Earlier it was F0, now they are operating at F dash. This is a primary control action, primary frequency control loop. The secondary frequency control loop will ensure that ultimately you need to restore the frequency to the 50 hertz nominal value, so that the further change in the valve output should be taken place by each of the generators, such that they will contribute and maintain the frequency at 50 hertz, because otherwise what will happen, there are so many frequency dependent loads, that is what we have told. The frequency dependent loads could able to operate at better, could able to show a better performance at F0 rather than at F dash, because F0 is what a rated frequency at which this motor is also designed for, right. So you need to bring back the frequency from F dash to F0. So for that you need to again change the governor output. That is what we have done in the previous here. This is what is taking care of that secondary control action. Frequency 50 hertz need to be restored, and that need to be also, again you see here, that need to be shared among the generators. How much valve need to be changed proportionately based on the capacity. So speed changer settings, this is what load reference for nominal speed, load reference set points. This is for nominal speed at no load, load reference for nominal speed at 50% loading, this is at 50% loading. You are just changing the governor set points basically from here to here. Load reference for nominal speed at 50% loading, you can see this is also there. So this is the overall block diagram. This is the overall block diagram. You can see here, this is a P reference, this is a load reference set point, and then there is a governor. First thing that will come is governor. From governor, this valve is adjusted such that the prime mover is rotated, and at individual level there is a different control transfer function that is being added. This is a transfer function of the governor, this is a transfer function of the prime mover. The output of prime mover is mechanical power output, that is compared with the loading input, that is load basically, and this is the rotating mass and the frequency dependence load. Finally there is a change in frequency, then that is connected with the droop characteristics and is reflected back to the first summation block. So the transfer function is output by input, that means delta omega s by delta PLS. So you will get this transfer function ultimately. If you do the transfer function analysis, you will get this. So what is the steady state behavior? So final value of the transfer function, that means t tends to infinity, that means s is equal to 0. This is the final value theorem, right? So s into delta omega s. So finally you will get this term. So, for several generators connected within the system, change in frequency is reflected in terms of cumulative effect of all the droop characteristics. This is with respect to one single generator. Multiple generators have their own droop characteristics, and there is also a term which is relevant to frequency dependent loads, D. So, this will decide the effect of the change in frequency with respect to change in load. So, with this we will conclude today generator control basics. Thank you very much.